Now, in grade 8, 9, and 10, you learned about quadrilaterals. Okay? Like a rectangle, a square, a rhombus, a parallelogram, and so on. A kite, those are quadrilaterals. Right? All quadrilaterals, they've got 4 vertices. They also have 4 lines that form that specific quadrilateral. Now, in circle geometry, we have got a special type that are called cyclic quadrilaterals. Now, the word cyclic, it comes from the word circle itself. So, a cyclic quadrilateral, it is actually a quadrilateral that has got its 4 vertices on the circumference. Okay, so if you see a circle, and then on the circumference of that circle, if there are 4 vertices, okay, on the circumference, then that quadrilateral is called a cyclic quad. The 4 points are said to be concyclic. Like in this case, right? This is extremely important. So, vertex A, vertex B, vertex C, and vertex D are concyclic, which means that they are vertices on the circumference of a circle. Therefore, they form a special quadrilateral which is called a cyclic quadrilateral. Okay? Now, there are about 2 main theorems on cyclic quads. Okay? So I'm going to move on to the first theorem on cyclic quads. Now, the first theorem, which is going to be our theorem 5, it says that the opposite angles of a cyclic quadrilateral are supplementary. And I'm sure you can remember from your previous grade that the word supplementary means add up to 180 degrees. So, the opposite angles of any cyclic quadrilateral add up to 180 degrees. Like, for example, if you add angle G and angle B, angle B plus angle D will give you 180 degrees. Angle A plus angle C will give you 180 degrees. So the opposite angles of a cyclic quad are supplementary. Now, the acceptable reason for that theory is this one here. You don't write the whole theorem, you just write opposite angles of cyclic quad. Okay? Now, if you go to the acceptable reasons on the page that I gave you, okay? Go to the acceptable reasons, you have to go to the next page. Okay, remember, I said under circles, the last 3, they are the corollaries of theorem 4. So if you turn the page, okay, right, you also have another one on, which is part of the corollaries as well. Now below it, that's where you see the theorem 5. Reason opposite angles of cyclic quads. The one that I underlined there, that's the reason that you must use whenever you see a cyclic quad. Okay? If you want to know that the 2 opposite angles of a cyclic quad are supplementary, you write the reason just like opposite angles cyclic quad. Okay, I would encourage you to indicate that on your acceptable reasons. Just write the theorem 5 so that you know where we are. Theorem 5. This is theorem 5 now. Okay? You turn the page, just write theorem 5. Alright? Okay, now the proof of this theorem is examinable. Okay, so I'm going to talk about it just now. The proof of this theorem is one of the 4 theorems in grade 11 that is examinable up to metric. Okay, it can come in this grade or it can come next year when you are in metric. Right? So far, I told you that theorem, the proof of theorem 1 is examinable, the proof of theorem 2 is examinable. Also, theorem 5 is examinable. The last one that we are going to do is going to be theorem 7. Alright? Alright. Let me carry on. Alright, so to prove here, you just want to prove that either angle A plus angle C is equal to 180 degrees or angle B plus angle D is equal to 180 degrees. Now, fortunately, the proof requires the use of theorem 2. Okay, so what you do is you construct two radii, that is AO and OC. You construct two radii. Because in this case, you'll be given the circle and the cyclic quad. Okay, that is the 4 points A, B, C, and D. The construction part, you have to do it yourself. Okay, so you join point A to the center, or you also join point C to the center, or. Once you do that, you are going to create two angles here at the center, that is O1 and O2. Then you apply your knowledge of theorem 2, that is angle at the center is 2 times angle at the circumference. So angle O1 is going to be equal to 2 times angle D. Our O1 is this one here. It's going to be equal to 2 times angle D. And our reason is theorem 2. Angle at the center is equal to the angle at the center is equal to 2 times the angle at the circumference. Also, angle O2 is equal to angle 2B. So O2 is equal to 2 times angle B. Again, this is a reflex angle. It's at the center. That's a reflex angle. It's going to be 2 times that angle B. Now, once you have got these two equations, right, or statements, you then add the left-hand side together and the right-hand side together. So you add O1 to O2, you add 2D plus 2B. Now, we know that angle O1 and O2 add up to 360 degrees, because they are angles around a point, or you can call it a revolution if you want, right? So when you add O1 plus O2, you get 360 degrees. Because of that, you can end up equating. I'm sure you can see there that if angle O1 plus angle O2 is equal to 2 times angle D plus 2 times angle B, and we know that this O1 plus O2 is equal to 360, so we substitute it by 360 degrees. Then we use our knowledge of factorization on the right hand side. We factor out 2, and we're left with 2 times angle D plus angle B. Then you divide both sides by 2. You're left with 180 degrees on the left, and on the right you're going to end up having angle D plus angle B, which means if you add angle D and angle B, you must get 180 degrees, which is what the theorem says. The opposite angles of a cyclic quad are supplementary. Alright? Now we can also do the same by creating or by joining the center to point D and the center to point B. If we do that, we can be able to prove that angle A plus angle C is equal to 180 degrees. Alright? You can do that as an exercise on your own. But be aware that when it comes to the proof, either they can ask you to prove that angle A is equal to, angle A plus angle C is 180, or they can ask you to prove that angle B plus angle D is equal to 180 degrees. So you need to be aware of how to prove either of the two statements. Okay. Any question there? Any question? Okay, so this is our theorem. Fine. Let's move on to the sister of that. Right. This one is just the converse. Okay. So the converse. Remember what I told you, that a converse is a reverse or an opposite statement which originates from the theorem. So the converse says if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. Okay? Right? So if you add any opposite angles of a quadrilateral, if they add up to 180, you can conclude that therefore that quadrilateral is a cyclic quadrilateral. Okay? Now the proof of this is not examinable, but we are going to use this converse to prove that any 4 points form a cyclic quad. We are going to do that later on. Okay? So we use the converse of theorem 5 to prove that a quadrilateral is cyclic. Okay? We use the converse of theorem 5 to prove that a quadrilateral is cyclic. We are going to do this later on. Okay? So here, you can just copy down up to there. The proof is not examinable. Just copy down up to there. Right. So an exterior angle of any cyclic quadrilateral is equal to an interior opposite angle. Now, what that means is, if you as you can see on this diagram, we have got cyclic quadrilateral A, B, C, D. Okay, but BC is produced such that we create this exterior angle. Okay, this exterior angle here. That exterior angle, it has been labeled as C1, and the one which is inside the interior angle is labeled as C2. Now, based on theorem 6, angle C1, okay, I'm sure you can see that C2, this angle C2 plus angle A, they add up to 180 degrees from theorem 5. Okay? And angle A is an interior opposite angle to angle C1. Therefore, C1 is equal to angle A. Angle C1 is equal to angle A. Angle A is called an interior opposite angle. To what? An interior opposite angle to angle C1. Yes.
So, what we work with theorem 6, it includes theorem 5 in it, so that follows all of them. So, like if you work with theorem 4, it includes theorem 3.
Yes. In actual fact, there is a connection between the theorems. Theorem 5 and theorem 6 are connected. And then if we start with theorem 2, right, it connects theorem 3. To a certain extent, it also connects theorem 4. And then the proof of theorem 5 comes from theorem 2. So the theorems are actually related. All right? Okay? Now, if I produce CB on the other side, like that, I can end up having here B1 here and then B2. Okay? So angle B2, or B1 rather, will be equal to angle what? Huh? Will be equal to angle what? D. Okay? Will be equal to angle D. Right? If I produce, say, AD from vertex A like this, so that I can create, maybe I'll call this one A2, that one A1. So if I say A2 is equal to what angle? It will be equal to what? C2. Okay? It's equal to C2 because angle A1 plus C2 give me 180. And A2 plus A1 will also give me 180. Therefore, A2 is what angle C2. Alright? Are you following what I'm saying? Right, so the proof of this, you use theorem 5 to prove theorem 6. Now, fortunately, the proof of theorem 6 is not examinable. But the reason is this: you write this exterior angle of cyclic quad. Now, you see that one on the acceptable reason, it's below theorem 5. Okay? Actually, no. It's below the converse of theorem 5. Okay? If you go to the page there, you have the opposite angles of cyclic quad. Then, below opposite angles of cyclic quad, we have got the converse. The converse of what? Of theorem 5, which is opposite angles of quad supplementary. Right? Now, I just need to emphasize this before I carry on. This one here, you can give this one as your reason. Opposite angles supplementary. Or you can write this one here as converse opposite angles of cyclic quad. Okay? Now I prefer this one. Okay, I prefer this reason. When you are giving the converse, I prefer that one. That's the one that I will be using later on when I'm proving that a quadrilateral is cyclic. Okay? So you see that below the main reason for theorem 5. So you've got two of them, opposite angles quad supplementary or converse opposite angles of cyclic quad. So I prefer converse opposite angles of cyclic quad. Right? Now below the converse of theorem 5, we have got our reason for theorem 6, that's exterior angle of cyclic quad. So we are here, we are back here now, theorem 6. Okay? Now after theorem 6, it also has a converse. Okay? Theorem 6 also has a converse. And the converse is if an exterior angle of a quadrilateral is equal to an interior opposite angle, then the quadrilateral is cyclic. Now this one here, the reason that I prefer for it is opposite. Sorry, I would say converse. Write converse first. Converse opposite angles. Sorry, it's converse exterior angle cyclic quad. Converse exterior angle of cyclic quad. Okay? That's the reason which is below the main reason for theorem 6. Yes? Alright? So when you use the converse of theorem 6, that's how you write it. And this word here is very, very important. That word converse. It's very important. Okay, I need to emphasize that. Also, for the converse of theorem 5, this word is extremely important. That word converse is very, very important. Okay? So the word converse is extremely important. Alright? The word converse is extremely important. When you are using the converses, usually of theorem 5, theorem 6. Later we are also going to use the converse of theorem 4 as well. We also have a theorem for converse, and the converse of theorem 7 as well. Okay. And also theorem for, we've got a converse for theorem 8. So a number of theorems, in fact all the theorems have got a converse. Okay. Alright. So here, I'm sure you can understand that if you prove, like in this case, that angle C1 is equal to angle A, okay? If points A, B, C, D are not on the circumference of a circle, you can conclude that therefore those points are concyclic. Hence, A, B, C, D is a cyclic quadrilateral. And your reason that you must give there is to say it's because of the converse of theorem 5, which says converse exterior angle of cyclic quad. Alright. Any questions before we go to some application?